Welcome to everybody. My name is Davide Spriano, and today I would like to tell you about hyperbolic models for Cat0 spaces. This is joint work with Harry Petyt and Abdul Zalloum. Okay, so let's start. Here is the 1-minute overview of the talk. Okay, so there are two classes of groups and spaces that have been very heavily studied in recent years, and they've been understood very well. There have been a lot of progress, and those are mapping class groups and Cat0 complexes. And one of the reasons of why those classes are so well understood is that they both have some very good gadget you can attach to them, which allows you to understand the geometry. For the mapping class group, those are the curve graph. And for the Cat0 cube complex, those are hyperplanes. Those are both some sort of like simpler object you can attach to understand the geometry of the space. But out of this picture, they have left out Cat0 spaces. So Cat0 spaces, instead of Cat0 cube complexes, are a much larger class of spaces and also groups if you look at co-compact actions of them, and there are no sort of, those tools have not really been exported to the class. And so for this reason, although Cat0 spaces are very classical and very well studied, in recent years, they got slightly less attention because we didn't really have those tools. And so the goal of this talk is to develop some curve graph-like objects, some hyperplane-like object, and try to convince you that those really are good objects by proving some theorems about them. Okay, so before we start, let me tell you a couple of words about mapping class groups. So for me, the mapping class group is the group of orientation preserving the isomorphism of a surface modulo the orientation preserving isomorphism, which are topic to the identity. And well, we know that it acts on the Cayley graph of the mapping class group, but most importantly, as I said, it acts on CS, which is the curve graph. And this is a graph which Mazur and Minsky, in a very important paper, showed that it is hyperbolic. And very briefly, how is the curve graph defined? It is defined as follows. We take our surface, for instance, of genus 2, and we have a graph where the vertices are isotopy classes of a simple curve, and edges, we put an edge between two isotopy classes if there are two representatives in the class that are disjoint. So for instance, now I have three curves A, B, and C, and if I would look at the portion of the curve graph spanned by those three curves, I would have an edge between A and B, but no edge between A and C and B and C, because no matter how you wiggle them around, you cannot realize those disjoint. Okay, so let me recall a very, very incomplete survey of result about the mapping class group. Is the following. Those are two results I would like to recall. The first one is due to Mazur and Minsky, that a mapping class phi is pseudo-Nozev if and only if psi acts loxodromically on CS. So there is this classification of mapping classes that need to be either periodic, reducible, or pseudo-Nozev. This is known as the Nielsen-Turnfeld classification. And Mazur and Minsky managed to prove that being loxodromic is completely characterized in terms of the dynamic of the action on the curve graph. Okay, and this is a very important and nice result. And another result, which is slightly older due to Ivanov, is that the automorphism of the curve graph, so we just now look at graph automorphism, simplicial automorphism sending edges to edges and vertices to vertices. This is naturally isomorphism to the mapping class group of a surface. And this is mapping class group plus or minus is because we now allow orientation reversing. In any case, the mapping class group is in index 2 in here. So really the curve graph encodes the combinatorics of the curve graph really encodes the geometry of the mapping class group. This is really a good object to study. So I assume you're all familiar with Cat0 spaces and Cat0 cube complexes. If not, or if you would like a refresh, please go and watch the previous video. And so clearly those two classes are different. Cat0 cube complexes have extra structure. It's easy to find some Cat0 space that is not a Cat0 cube complex. But what about when you talk about group action? Is really the class of groups that act geometrically on a Cat0 cube complex, is this really different than the class of groups that acts geometrically in a Cat0 space? Because we are trying to develop some new tools for cat-zero spaces, and this would not be very interesting if the class of group acting on cat-zero spaces would be exactly the one that acts on cat-zero cube complexes. But then this is not the case. So let me recall some theorems. So there are a sequence of theorems. The first one is due to Katzan, and then many other people afterwards add various cases, is that if we take uniform lattices in higher rank simple Lie groups, those act geometrically on cat-zero spaces and have P. So we have a very large class of extremely natural example of group that acts geometrically on cat-zero spaces with P. But then a theorem of Niblo and Reeves shows that any group acting geometrically on a cat-zero cube complex does not have P. So those are all groups that are cat-zero, but not acting on cat-zero cube complexes. So those classes, really, there is a difference between the two of them. And let us recall what's the goal of this talk. We want to somehow extract hyperbolicity. We want to somehow get an object which is like the curve graph, so some sort of hyperbolic object, hyperbolic model for our spaces that gives us the hyperbolicity. And in cat-zero cube complexes, we had such a space, the contact graph and the generalization introduced by Genoa. And this is a procedure that you input a cat-zero cube complex and outputs a hyperbolic space and depends over some threshold that tells you the hyperbolicity. However, in order to carry over such a technique, we need something that like hyperplane. And the issue is that in general cat-zero spaces, we don't have hyperplanes. So let's solve this issue and let's try to define something that reminds us of an hyperplane. And the notion is the notion of curtain. So the definition is as follows. We take a cat-zero space X, we take gamma a geodesic, and we take P a unit interval in gamma minus the endpoint. So this means a subsegment of length exactly 1, which does not contain the endpoint of gamma, which is in the interior of gamma. Then a curtain is the set C, which at the point in X, such that the closest point projection of such a point lies in P. So pictorially, this is gamma, this is P. We sometimes call P the pole of the curtain. And then any point in the space, such as the closest point projection on gamma lies in P, is in my curtain C. Okay, and naturally, curtains determine two half spaces, C plus and C minus. Like we take an orientation, a direction on a geodesic, and then C plus are all the points that project after P, and C minus are all the points that project before P. So half space is in quotation mark because C plus and C minus do not cover the whole space. You need to have C plus, C minus, and C. So it's really a tripartition to be precise. But the idea is that a curtain really separates the space in two. Like what's left is two components. Okay, and now let me go to some examples. So if we take R2, the old Euclidean 2 space, well, we have many curtains whenever we take, for any geodesic, for any unit interval on the geodesic, we just take curtains, and curtains are just strip of unit width, that those are all the points whose closest point projection on such a geodesic would lie in the pole. And so these are 3 examples. And now let's take another example, the tree of flat. So this is the universal cover of a torus wedged to a circle where the torus is a flat torus. So those are really Euclidean flat. And now what happens if I take, for instance, this geodesic and a unit interval onto it? Well, on the Euclidean part, I know what's going to happen. I'm just going to have a strip. But if this strip contains one of the branching points of the tree, then everything in that branching point will be contained in the curtain. And so curtains are really different from hyperplanes. There are some fundamentally sorry, there was an interruption. So let's now consider X to be the space obtained as the universal cover of a torus wedge a circle, and the torus is really a flat torus. So that sorry, there was an interruption. So when I consider a curtain, I will really contain all of the branching, all of the part of this sphere flat that is attached to this branch. And this is really a big set. So for instance, contains ball of arbitrarily large diameter. So in some sense, curtains are very different from hyperplanes because hyperplanes are in some sense one-dimensional and very well behaved, whereas curtains are much more complicated. And this is really the point of like this project, that although this notion is very natural and it looks like similar to hyperplanes, in practice is quite harder to work with because you need to take care of a lot of those issues. But luckily you can take care of many of those issues. Okay, so those are some examples of curtains. And now let me introduce some very important notions of like, how do we consider a set of curtains? So the notion of set that we want to consider is the notion of chain. So we say that the collection C1, Cn is a chain if all the elements Ci are disjoint, and the following happens is easier said in a picture than in practice. They are arranged in this way, like in a chain, and not facing each other. So to be more precise, if I now take the half spaces of those curtains, there is an ordering and a selection of half spaces such that they are a chain under inclusion. There's just one inside the other. Okay, and this is the most technical definition of the talk. We say that a chain is L separated if for every Ci and Cj, so for every pair of curtains in the chain, every other chain that intersects both has size at most L. So in picture, for instance, in R2, if I take any two disjoint chains, so you quickly figure out that disjoint means it needs to be parallel, otherwise they would intersect, then they will never be L separated because I can always find an infinite collection, an infinite chain that intersect both. Whereas if my space is more hyperbolic, it might happen that my curtains C1 and C2 somehow only go together in some small area such that I can only fit L, a chain of length L between them. Okay? And so we use this notion to define a distance, which is fixed L, and we define a new distance, that the L between xy different points. If they are the same point, we put it to be 0. Otherwise, is the size of the maximal L chain separating x from y plus 1. Okay, so first question is y plus 1. Well, this is just essentially because the curtains are thick. So what does it mean? It means that if I have x and y that are separated by a curtain, then their distance in x in the original cat0 space is at least 1. Why? Picture, so if these are x, this is x, this is y, this is a curtain with a pole that separates them, then any geodesic connecting x and y, if I take the first point that enters the curtain, the last point that enters the curtain, I take the closest point projection of the geodesic, and since poles have length 1, the distance between the projection of A and B will have distance 1. And since closest point projection does not increase distances, this segment will have length at least 1, and so the distance between x and y is at least 1. Okay, so curtains are thick. So if we would not add this plus 1 or like some sort of other artificial, we cannot just take this number, because this number would put together points that are too close to each other, because you can just not fit any curtain. And the theorem is the following. The function we defined above is a metric in D. The space XL, which is X with this metric, is hyperbolic, and on top of that, every isometry of your original cat0 space is an isometry of your new space XL. Okay, let's see some examples. For instance, if we now take Euclidean plane, and now we take 2 points, if the distance of 2 points in the Euclidean plane is at most 1, then we cannot fit any curtain separating x and y. Is this picture. Whenever I try to pick a curtain between x and y will be in the curtain because they are so close. The distance between x and y is 1. Otherwise, the distance is 2, because I take x, I take y, well, sure, I can fit a curtain between them. But then whenever I try to fit a second curtain, those two will not be L separated for any L. There will be an infinite chain that crosses both. So the distance is going to be 1 plus 1, that is 2. Okay? And on the other hand, if we start with a hyperbolic space, then the identity from X to XL is a quasi-isometry for large enough L. So those are the two ends of the spectrum. On one side, the spaces are always bounded. On the other side, you get what you started with. And it is not surprising that the space for the Euclidean space is bounded because there is no hyperbolicity there. So you don't expect to see anything. Okay? And so now let's get to the theorems. If I have a group G that acts on a Katsira space semi-simple, and I have a group element, the following are equivalent. G is rank 1. If and only if there exists some L such that the morbid map into XL is a quasi-symmetric embedding. And this is very reminiscent of the mapping class group, where an element is pseudo-knows of if and only if it quasi-symmetrically embed in the curve graph. And also, this provides you many examples of spaces where this XL is unbounded. As long as you find one rank 1 element, you will find an unbounded space. And this is the same. And in Katsira cube complexes, there is a notion of rank 1 if and only if, this is due to Caprassa give, an element G is rank 1 if and only if G skewers two separated hyperplanes. So what does it mean? Skewers, I have C1 and C2 that are separate, and G sends C1 after C2. Okay? So this is a characterization for Katsira cube complexes using hyperplanes, and we recover exactly the same one. So there exists L such that G skewers to L separated curtains. We get this characterization in terms of one element in terms of curtains. And then you ask yourself, okay, so we have some notion of where those spaces are unbound. With a rank 1 element, we find that those spaces XL are unbounded. Well, what can happen? So let's take a group G that acts on a Katsira space geometrically, and then we have exactly one of the following. Either G is a rank 1 element, which means that G is virtually cyclic, or it is acylindrically hyperbolic. And because the action on those XL, which now is unbounded, because the rank 1 element gives us some unbounded direction, will witness acylindricity. This could be one reason. Actually, having a rank 1 element is a theorem of Alessandro's sister that shows us that the group is acylindrically hyperbolic. Or G has linear divergence, which means that no cut points in an asymptotic cone. So whenever you take an asymptotic cone, there are no cut points. It is also to say the definition of this fact is being wide. Okay, so there is this dichotomy. And then let me conclude with a theorem that I like very much, which is an Ivanov type theorem, which is the following. Let X be a proper Katsira space with the geodesic extension property. So this means that whenever I have a geodesic segment, I can extend it to a by infinite geodesic. And then suppose we need some additional hypotheses. Suppose that either X admits a geometric action by a group that is not virtually free, or X is a tree of valence at least 3, or X is one-ended. These cover a large class of groups. Then, if any of those happens, then the isometry of X are the same as the isometry of XL. So every isometry of XL comes from an isometry of X. So the combinatoric of XL, that's just the geometry of this hyperbolic space, is the dynamic of this hyperbolic space is the same of the dynamic for your hyperbolic space you started with. And this is everything I wanted to say, and I thank you very much for your attention.